this is Mr. Keister back with you today to do lab 2, which is about it's actually been in school all the time. I believe Chem 2 today we'd have been doing on the 15th. For honors Chem, it was probably 5 days after that, around the 20th or somewhere around there. In any case, just to remind you, original Chem or we instead, or you instead, I should say, page where you links to our house on homepage, as well as keys for all the assignments that are being completed through semester 2, and also links to these videos. So, anyway, said all that. Let's look at E11. So, this unit 2, we have been. Sorry about that. You know me and technology, not the greatest. Anyway, in Unit 11.2, we've been talking about electrochemistry and redox reactions, and in particular, these last, let me think, 3 or 4 lessons, we have been talking about Voltaic cells, what they are, how they are set up, and what they are used for in terms of modern everyday life. In fact, we've said many times just how valuable a redox reaction, in particular a voltaic cell, is utilized to provide electrical energy to many of the devices that we depend on in today's society. And so this lab, as we look back here, in this experiment, we're going to prepare several different half cells. In other words, we're going to set up half reactions in these little compartments here. I don't know if you can see that, but hopefully you can. Setting up a half reaction in each of those compartments, and then we're going to link them together using a salt bridge, which again maintains neutrality in each of the solutions. And we're going to hook them up to a voltmeter, which will then I'll connect one clip to one metal in one of the half reactions and the other clip to the other one, and get a voltage reading, which will show then that the electrons are indeed transferring from the anode compartment, which is where the oxidation and the release of electrons occurs, over to the cathode compartment, which is where those electrons are used to produce another substance. And of course, if this voltmeter was a device that utilized the electrical energy as the electrons pass through it, and that of course would be representative of things such as, you know, a cell phone, a flashlight, or anything else that takes batteries in order to operate. So there was a pre-lab assignment with this one that asked you, basically reviewed all the things we've talked about in regards to redox reactions in voltaic cells. So here I have listed 4 half reactions, reduction half reactions. As you can see, they're all in reduction, just as they were on the chart. In fact, I pulled these off of the chart that we've been looking at all this unit and listed their values here. I'm going to go over a few of these questions, not all of them, but just as a review to what we've been talking about. Question A, offer an explanation as to why the values for the listed 4 metals vary the way they do. So as you can see, silver has a positive value of 0.799 volts, which says that it reasonably wants to be reduced, all right? But then as you go through aluminum, barium, and lithium, you can see that the values of E become much more negative, and in fact are negative, which tells us that these 3 substances would rather not be reduced at all, but instead in the reverse reaction, that these three metals would prefer to be oxidized. So why do they vary? Well, they vary due to, number one, their locations on the periodic table. And in particular, as we talked about in multiple units, their location on the periodic table affects several things, all right? First of all, it affects their number of valence electrons. Their ionic or atomic size, all right? Their ionic and atomic size, their electronegativity, ionization energy, electron affinity, all of those things, which are then going to determine how much a substance wants to be oxidized or reduced. So here again, their location on the periodic table is key when looking at the difference in the values of E for these various half reactions. Letter B asks, which metal ion is most easily reduced? Okay, so something wants to be reduced, it's going to have a more positive value of E. And so given these four, silver not only is the most positive value of E of these four, but it's the only value of E of these four that is positive. So the silver ion then wants to be reduced the most. And letter C, which one is most easily oxidized? Well, the one most easily oxidized wants to be reduced the least, of course, meaning its E value then would be the most negative, which of course would then be lithium. And so lithium metal wants to be oxidized the most. And then in question 2, it says that the silver and the lithium electrodes are connected as a voltaic cell to make a battery. All right. So we're using this one here, silver, and the bottom one, lithium. So question 2a, which one is the anode? Okay, well, the anode then would be the one that wants to be what? Well, it would be the one, what occurs at the anode? Oxidation occurs at the anode. And so we want the one that wants to be oxidized the most of those two, or the most negative. And of course, that would be lithium. All right. So it is the most negative. So it wants to be oxidized. Or you could say it does not want to be reduced. And then for the same line of reasoning, which one is the cathode? That's the one that wants to be reduced. Remember, reduction occurs at the cathode. And so of those two, the one that has the most positive value of E, of course, is silver. All right. So silver then, E is most positive, wants to be oxidized, or I'm sorry, wants to be reduced. I think I'm going to let the rest of these go for you to do on your own. So we're to set up your two half reactions. Remember, reduction occurs at the cathode, oxidation occurs at the anode. We know which one goes which now. So set up your two half reactions accordingly. And then given the values of E that we're working with and the way that we calculate E cell, which remember we calculate it by taking E reduction cathode minus E reduction anode. Cathode minus anode. Remember on the oxidation reaction, you do not have to change the value of the sign because subtracting the two rather than adding. So I'm going to let you finish those questions. Very similar to what we have already done in our discussion of voltaic cells and on our homework. So let's go to the next page, which is where the procedures are. So let me up here and erase this. so as we look at part 1, we're going to prepare a reduction compartment by adding approximately 2 mLs of copper 2 nitrate solutions, so this is copper plus 2 ion, to one of the center wells of a 24 well plate. Then add about the same amount of lead 2 nitrate to an adjacent well. Take a strip of copper and place it in the copper solution, and a strip of metal and place it in the lead solution. Again, I don't know that you can see this very well. I'm trying to hold it a little bit without spilling it. So here are my two half reactions under number 1. My copper 2 solution and my copper metal are in this well. My lead 2 solution and lead metal are in an adjacent well. Then take a small strip of filter paper that has been soaked in potassium nitrate and drape it across the 2 wells so that one end dips in the solution in each well. So this is our salt bridge. So here I have some potassium nitrate 3 solution, and I put some strips of filter paper in it yesterday and let them soak overnight, so they're good and soaked. And hopefully you can see that I have a piece of KNO3 soaked filter paper draped between the 2 half reaction compartments so that it is touching both solutions. So we now have a salt bridge established between the 2, which will allow for the continuous flow of electrons from anode to cathode. Then on number 4, we're right here. Connect one lead from the voltmeter to the copper strip and the other to the lead strip. Turn the dial from the off position to the number 2 and read the voltage between the 2 compartments and record. Okay, so this is a voltmeter again. So I'm going, it has 2 leads on it, one for positive, one for negative. I'm going to set it to 2 like the instructions say. And I'm going to go ahead and hook up one of the leads to the lead metal and one of the leads to the copper. And lo and behold, in doing so, and again, I'm sorry, you probably won't be able to see this, but maybe you can at least get a quick glimpse of it. You flip it around there, that my reading is negative. Well, if the reading is negative, if the voltage is negative, then what have we done? What have I done wrong? Well, what I've done wrong is connect the leads backwards. So what I'm going to do here, let me get that back in there where it belongs. There we go. Dry it off. Guess I should put my goggles on too. Breaking all the rules here. My bad. Oh, there we go. Okay, so what I'm going to do is just reverse the leads. There we go. And I'm getting the exact same reading I had as before, only now it's positive, which means that we have now an operating cell where the electrons are flowing as they should from anode to cathode. Now, I will say this, and this is doing this right now. It's flipping back and forth on me. I'm sorry if you can't see that, but the number's flipping back and forth on me. It's not a constant number. Well, several reasons for that. Number 1, I'm jiggling this thing. I'm not too steady with my hands anymore. Number 2 is as these electrons are going from the anode compartment through the wire, through the voltmeter where it then gives us our reading, and back through the other wire and into the reduction compartment, those electrons are hitting atoms or particles with it that compose this wire, the voltmeter, and this wire here. So there are obstructions along the path. It's not a clear path. It's not a clear path. Like, you know, sometimes you're out driving and there's no one else on the road except you, and it's clear sailing all the way. Other times you might be driving on the interstate, and there are cars and trucks everywhere, and so you're weaving in and out of traffic from right lane to left lane so that you don't hit all those things. And in doing so, you end up slowing down, speeding up, slowing down, speeding up. This is the exact same thing here, all right? As the electrons are passing through the wires and through the voltmeter, they are encountering obstructions along the way that they have to zigzag around. And so the reading is not a solid definitive singular reading. So what I did is, let me take these off for a minute. What I did then in recording the value is just kind of looked and see where it was flashing around on the most, and gave my best guess. And in doing so, my measured voltage here, this is for number 1 right here, was 0.470 volts. It actually jumped around from about 0.515, or it goes out 3 decimal places, by the way. It actually jumped around from about 0.515, 0.520 down to about 0.450, 0.445, somewhere in there. So again, I gave my best guess as to a happy medium there. Excuse me, and went with that. Now I have compartment 2 set up the same way, only now compartment 2 is copper and zinc. And I haven't set up compartment 3 yet. I'll do that right now so you can actually see what I did. So in reaction 3, we have zinc as one of our half reactions and lead as the other one. So here is a piece, let me scoot that out of the way. So here's a piece of zinc, and I'm going to put zinc solution. It's actually zinc nitrate. And these are all 1 molar, by the way, which is the standard. Remember, in standard conditions, all solutions are 1.0 molar. All of these solutions are 1.0 molar, so we are standard. As far as temperature, we are at room temperature, so we're standard there as well. There are no gases involved in any of these reactions. If there were, our pressure in our room is very close to 1 atmosphere. So we're good, give or take, within a little bit here or there of standard conditions. Although we're not exactly at standard conditions in terms of temperature or pressure. So that, again, that could affect our values just a little bit. So let me go ahead and put zinc solution in the zinc metal compartment. Did that. And then let me put lead 2 solution. It's actually lead 2 nitrate in the lead compartment. There we go. And then I'm going to go ahead and fish a salt bridge out of this potassium nitrate solution. There we go. And drape it between the 2 compartments such that it is touching both solutions. So we have all 3 voltaic cells set up. Let me go ahead and get a reading on the other 2. There we go. That one's not reading negative, so I got it hooked up correctly. Remember, we'd automatically, you should know this from our lessons, that the one that's the more positive value of E, the half reaction that has the more positive value of E, that's the one we're going to set up again as the cathode. And then that's the one that's getting reduced. So that's the cathode half reaction. The one with the smaller value of E would be the anode half reaction. So again, knowing that ahead of time, it kind of helps to not make a mistake of putting the electrodes on the wrong ones. But if you do, no big deal. You can just switch them. This one is a much higher voltage. Let me see. It's flipping back and forth on me. Let me give my best guess there. Let me release that. Looks to me like around 0.96. So again, to go to 3 decimals, 0.960 volts on the second one. And now there we go. It's cleared back to 0. By the way, it's reading 0 now because it's not hooked up to anything. Let's do the third one. The third one is zinc and lead. All right, and there we go. Got that one hooked up correctly too. It's reading somewhere, the low is about 0.427. The higher is about 0.4, how high is it going? 0.44, 0.45, 0.44. Okay, let's undo that, cut that off. take these off. And again, based on my best guess, the last one is right at about 0.438 volts. Okay. So I'm going to focus now as far as the data table and the calculations on reaction 1, and then those procedures you would follow in the same way to do reactions 2 and 3. I'll have you do that on your own. But anyway, so as I look at reaction 1, copper, remember this was copper plus 2, and this was lead plus 2. If I look up the two half reactions for those two electrodes, I see that copper has a more positive E than does lead. So then I know for a fact that the copper one is going to be my cathode half reaction, which is reduction, and my lead half reaction will be my anode. So that will be my oxidation half reaction. Okay, so before we do this, we're going to go down here and look at the calculations. Then we're going to flip actually to the last page of the lab and to show our work there, and then do our finished one, finish this one off here. So in the calculations for part 1, standard EMF, it says for each of the Voltaic cells you set up above, write the reduction and oxidation half reactions at each electrode, respectively. Write them on the back of the last page, spaces provided there. And then the data table above, write the balanced net ionic equation for the Voltaic cell. Okay, so let's let me get this out of the way here. Set that over there. There we go. I'll be needing some of that again here when we get to part 2. So let me advance this, and we're now on the last page. All right, so we're going to go ahead and do reaction 1 together. So reaction 1, again, was copper and lead. We just said, now I've got my reduction potentials chart right here. And again, as I said a minute ago, when I look up the half reaction for copper, it is more positive, copper 2 that is, it is more positive than the half reaction for lead. So our cathode reaction, which is reduction, and our anode reaction, which is oxidation, are going to be copper getting reduced and lead getting oxidized. So if I look this up, for copper plus 2 now, going to copper metal, there are several copper half reactions here, and it's actually the first one, where copper plus 2, AQ, is going to copper solid. That's the one we want. So our half reaction here is Cu plus 2 AQ plus 2 electrons yields Cu solid. And pulling that value off the chart for E is 0.337 volts. Okay? This is a whole lot like the problems we did on the lessons and on your homework, so hopefully this is looking pretty familiar to you by now. So our anode reaction involves lead, all right? Now again, on here, the lead half reaction is going to occur as a reduction, so we're going to be flipping that in reverse. And so on the right-hand side, about 3/4 of the way down, here are lead plus 2 half reaction with lead solid. Again, I'm going to reverse it around and make it an oxidation half reaction. So this PV solid going to P plus 2 AQ plus 2 electrons. And the value of E for that, and again, I'm not going to flip the sign. I've talked about this many times. Since in our calculation of E cell, we subtract anode from cathode, we do not have to change the sign on our oxidation half reactions. That value is minus 0.126 volts. So, our overall net ionic equation. Well, as you can see here, the number of electrons transferred is equal. So we will not need to multiply either or both of those half reactions by an integer. And even if we did, remember that that does not change the values of those E's, because again, voltage or cell potential, E cell, or E values are intensive properties. They are not. They do not vary by quantity. Okay, so E cell then. Well, let me write the net ionic equation first. So these are going to cancel. So we have Cu plus 2Aq plus Pb solid yields Cu solid plus Pb plus 2Aq. This is the net ionic equation then that is asked for on the data table for part 1, reaction 1. It's right there. Right there it is. Okay? Now, let's calculate E cell for this. So E cell equals E reduction cathode minus E reduction anode, which is 0.337 minus negative 0.126. I'm a little crowded over there. Sorry about that, because I wanted to leave that up. And so that value of E is 0.463 volts. All right? So let's make a return trip there and finish off the first reaction. So we had said previously that the measured voltage for reaction 1 was 0.470 volts. We said that our copper half reaction was our cathode, which was reduction. Our lead was anode, which was oxidation. The ionic equation for this reaction, for this voltaic cell, we just determined a little bit ago. I'll rewrite it here. Pb solid plus Cu plus 2Aq. Of course, these can be reversed around. Yields Pb plus 2Aq plus Cu solid. So the work for this we, of course, showed on the last page. Then we calculated E cell. That is our predicted voltage. That is the theoretical voltage that this voltaic cell should produce. This is our actual right here. So that was 0.463 volts. As you can see, it's not bad. All right, it's definitely within reason in regards to error. So based on the two values we got for here, I want you to do the same thing with these two reactions on the last page, and then fill in the rest of this. Same procedure. All right, now let's go to part 2. EMF at non-standard conditions. Excuse me. Again, standard conditions for voltaic cells are room temp, 25 Celsius, gases, standard pressure, 1 atm, and solutions, 1.0 molar is their concentration. All right. Within reason, like I said, the conditions that we ran our first set of reactions in part 1 could be called, or should be called, a standard condition. Now we're going to vary something here. So we're going to dilute 1 molar copper nitrate solution by adding 2 drops to a small test tube and then adding 18 drops of water. Okay, so take my copper solution here, put my goggles back on. All right, and I'm going to put 2 drops there. 1, 2, and then I'm going to add 18 drops of water. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10. 11, 12, 13, 14, 15, 16, 18. All right. So I now have 2 drops of copper nitrate solution in 20 drops of solution total. So 2 over 20 is the same as 1 over 10. So I have now reduced the concentration of this copper nitrate solution to 1/10 of what it originally was. So originally it was 1.0 molar. It would now then be 0.1 molar, as it says right here. I'm going to do that again. So now I'm going to take 2 drops of my 0.1 molar. One, two. I'm done with that. Put the rest of that back in there. And then I'm going to take 18 drops of water. 8, oh, one more, 18. There we go. Well, you can see the light blue color is really fading quickly. In fact, it's barely blue. All right. And now I'm going to take 2. So now this has been reduced to 1/10 of what it was here. So here it was 1/10 molar, and now here it's down to 1/10 of that, which is 1/100th molar, or 0.01 molar. So I'm going to, let's see, am I supposed to do it again? Yes. I'm going to do that one more time. So I'm going to use this one, my copper nitrate one. I'm going to take now 2 drops of this one and put it in a new test tube. There we go. There's that. 18 of water. All right. All right. Well, I can't see the blue now at all, which isn't overly surprising because, well, I had 0.01 molar here, and now this concentration is 1/10 of that. Again, 2 drops to a total of 20 is a factor of 1/10 or 1/10. And so now this concentration of copper nitrate is now down to 1,000th of a molar, or 0.001 molar. Now, I'm going to add 2 mLs of this 0.001 molar to a well plate, use the regular 1 molar lead nitrate solution to an adjacent, and set up another voltaic cell. Okay, so let's do that. So I'll bring back my thing here. Take this, put it in one compartment. A little more. There we go. Done with that. And now in the other compartment, we're going to do lead, only now this is still 1 molar. So basically what we're doing is we're repeating reaction 1 from part 1, only now reduced concentration of copper ions in our reduction half reaction compartment. So what does that mean? Well, what it means is we're now at non-standard conditions. So let me take a piece of paper towel. I will wipe off our copper electrode metal, put it in the copper solution. I will wipe off the lead piece, put it in the lead solution. I need to get a new salt bridge here, which I will grab one, maybe. There we go. Only need 1 though. And I dropped it, of course. There we go. And I will drape it between the two compartments. Perfect. Again, allowing for the continuous electrons between the two. Turn my voltmeter back on here. Let's see, I think I remember how to do this. Yep. And set this up. There we go. Well, the voltage has gone down a little bit. And it's flipping back and forth on me. Pretty dang close to 0.42 though. It jumped up to about 0.435, but it jumped down to around 0.410. No, 0.409, 0.432. Okay, let's release that. Cut it off. Take these off. Scoot this out of the way. All right. We are going to go ahead and record that measured, or that actual voltage, as 0.420 volts. Okay? All right. So when we calculate E at non-standard conditions, we have an equation that allows for the correction in the difference in our conditions. All right? And that is called the Nernst equation. This was, I believe, on the last lesson we had on in Unit 11 too. So our calculations for part 2, using the Nernst equation, calculate the predicted voltage, E, from the Voltaic cell above. Compare this to the measured voltage and calculate percent error. Okay, so first of all, let's recall that we're using the same reaction that we used in reaction 1 of part 1. We already have our net ionic equation for that. I'm just going to go ahead and write that again. So this was the net ionic equation for this Voltaic cell, which was number 1. So we had PB solid plus Cu plus 2Aq yields PB plus 2Aq plus Cu solid. And E cell for that, the theoretical value, again, this is from our calculations in part 1, was 0.463 volts. All right, 0.463. So the Nernst equation. So the Nernst equation says this: E at non-standard conditions, all right, is equal to E cell at standard conditions minus. Okay, now our correction factor is simplified here. I talked about this in our last lesson. Is because we did run the reaction at 25 Celsius or room temp. We didn't have any gases involved, but we were at standard pressure. And so the correction factor for the Nernst equation, when we keep those two things the same, reduces down quite nicely. And it's 0.0592 over N. Remember, N now is not moles. N is the number of electrons transferred in the Voltaic cell times the log of Q. Remember what Q is, all right? So Q is the ratio of product concentrations to reactant concentrations, all right? So remember, solids are not included in the calculation of Q. So we're just looking at these two solutions right here. Well, remember our lead solution, we kept the same, all right? We kept it the same. It was 1.0 molar. Our copper solution, though, our copper 2 solution, though, remember that we diluted it several times and ended up with a concentration of 0.001 molar. So we'll want to remember that. So I'll do that over here. So Q then, hopefully you can still see me. Q then is products, concentrations over reactants, raised to some power. Remember, if we have a mole coefficient in the equation of other than 1, then that coefficient becomes an exponent. Here, we're all in a 1-to-1-to-1 ratio, so that doesn't really affect us here. So our product then was our lead plus 2 concentration. Our reactant is our copper plus 2 concentration. So we have 1.0 over 0.001. And so Q then comes out to be 1,000. Okay, 1,000. All right, now we can calculate E. So E is equal to E cell, which is 0.463, minus 0.0592 over N. Oh, if you remember from your back page when we did our net ionic equation, when we put our two half reactions together, the transfer of electrons was equal to 2. So this N would be 2. And then also times log of 1,000. So now we're just going to do the math. So that's equal to 0.463 minus 0.0592 over 2 is 0.0296. And the log of 1,000, base 10, is actually 3, since it's 1 times 10 to the third, if you remember what log base 10 means. And so 3 times 0.0296 is 0.0888. And so E now comes out to be, and I'm not going to do any rounding, remember. We talked about that earlier, 0.3742 volts. All right. So this is our theoretical value for E at non-standard conditions. All right. This was our actual value of E at non-standard conditions. And so you will use these two values to calculate percent error, which you should know how to do. Okay? Actual minus theoretical over theoretical. Remember, this is our theoretical value of E at non-standard conditions for this reaction, and this was our actual measured value of E that we got with our voltmeter. So I think you should be able to finish this up. All right, finish this up. Do the rest of the data table and calculations in part 1, and then do the rest of the calculation and answer the questions here in the discussion. So I think that takes us to the end of lab 11.2, which is on voltaic cells. Again, voltaic cells play such an important role in our daily lives now. We have so many devices that operate off of batteries and other types of voltaic cells. They are major importance to our very advanced technological world that all requires electrical energy to run those devices. So anyway, that's it for today. This is Mr. Keister. Until next time, take care, everyone, and I'll see you soon. There we go. Catch you later.